Okay, so here's an example. Let's imagine we're given a totally square field, 40 acres, same length and width. It's Webster soil. It's got a totally uniform slope that's actually diagonal, resulting in a 0.5% slope in this direction and a 0.5% slope in this direction, and we don't need any surface drains. So, and then we have an outlet down at the bottom corner right here. So first question we need to ask ourselves is, how are we going to lay out this drainage system? Now, the field that I have just described would have contour lines that look like these red ones, in which case we would put the laterals parallel to here and maybe a main line that goes, well, we got to have a lot of main lines because if we put these perfectly on the contour, which direction will the water flow? So maybe we'd want to do something that was kind of like more of a herringbone style. We get some water flow into there, and then a main line down here. It's a little bit complicated. Each of our laterals is going to end up being a different length, and that's going to get weird. So we might elect to just do something simple like this, where the outlet's down here. We're just going to run the main right down into the outlet. It's on a 0.5% slope. The laterals are on a 0.5% slope. It's a little bit counter to the guidelines that I gave, but it makes the layout a lot more simple. So we might do this instead. And then it's certainly going to make our math in this example simple. So this is the layout that I'm going to choose for this particular case. So first step is going to be figure out what the spacing, the depth and spacing is going to be. So I go to the Iowa Drainage Guide, and I was given it's a Webster soil. So I look up a Webster soil, and it says, are you sure you don't need surface drains? Because you might need surface drains or intakes into that tile. But let's say I don't. I drew a very phony sort of field that it's like a flat plane. There's no topography or depressions in it at all. So, okay. I'm not going to use surface drains. So then the question is, I'm going to use a 36-inch depth or a 48-inch depth. Now, if I'm doing this problem for myself, I would probably choose a 36-inch depth because I know that's slightly better for water quality. But let's say my client's like, no, I'd rather pay money to have a deeper trench than to have more tile lines in there. And so let's say there's a reason we're going to have a 48-inch depth. And so I'm going to choose something just right in the middle of this range, a 90-foot spacing. Maybe I have some reason that I did that. Okay, so then I need to select a drainage coefficient. And I'm looking at, this is central Iowa, so we're almost certainly in field crops. We don't need any surface inlets. So we'll say that's good surface drainage. That's totally flat. Water ought to just roll right off there. And it's a mineral soil as compared to an organic soil, which would be like a peat kind of soil. So I would be looking at a drainage coefficient of 3/8 to a 1/2 inch per day. I'm going to choose, just in this example, the large end of that range. That allows a little bit more capacity for maybe adding some surface drainage later if we decide that we need it. So now I can move on to the part where I am computing the diameter of those lines. But first I got to figure out the flow rate through here in CFS. So it's that drainage coefficient times the drainage area. So in this case, it is the spacing that I have selected. Because remember, if I'm looking at a system like this, here's my main, and then here's my laterals. If these are at a 90-foot spacing, that means that each one of these is draining essentially this amount. So where this is, 90 foot, and then this is whatever that is. I'm imagining that I'm going to put this at half the spacing so that this distance is 45 feet. So when I actually compute this, I'm kind of subtracting off that 45 feet. Each the sides of this 40-acre area is 1320 feet, which you could figure out using your calculator. So that the area of each one of these laterals is going to be draining the spacing times the length of this little area here. So at a 1/2 inch per day. So I've got a 1/2 inch per day for the drainage coefficient, and 90 times whatever 1320 minus 45 feet is for the square feet of the drainage area. And then I am just doing some unit conversions to get this into cubic feet per second, because I know that's the units that I need when I move on to the equation for tile diameter. So here's my capacity in CFS of each of the lateral lines. Now I got to figure out the Manning's roughness coefficient. So many of the references on drainage system design will have a table that describes Manning's roughness coefficients for different types of drains. So corrugated plastic tubing here are these three, and you can see that we've got different values for different pipe diameter ranges. I know enough about how this is going to turn out that I'm pretty confident before I even get started that I'm going to land in the 3 to 8 inch range. But let's say that I was wrong and I picked the Manning's roughness value that corresponded to the 15-inch tile diameter, and then I calculated I only need 4. That I would just go be like, oh, 4, okay, go back, correct the Manning's roughness value, and redo those calculations, just one quick iteration. But I'm going to imagine that I'm going to land in the 3 to 8 inch diameter range, so I'm going to pick a value of 0.015 right off the bat. So there's my Manning's roughness value. So then I'm going to just stick that information into this equation. So here's the Q that I calculated. There's my Manning's roughness. I was given a slope along the, so we're doing the lateral, so the slope along the lateral line that is in the east-west direction, it's a 0.5%, so 0.5 divided by 100. So, and then that whole quantity time to the 3/8 power, crunch that up, and I get 3.01 inches. Now, I told you earlier you should always round up, but I'm going to take a chance on that 0.01 inch, that maybe that's not that important. And also, I had chosen a drainage coefficient that was on the large end of the range, so I'm not taking too much of a gamble. I'm not gambling that I'm going to end up, if I make the tile line just a tiny bit smaller, that I'm somehow now totally out of whack on my recommended drainage coefficient. So in this case, that's close enough. I'm going to use a 3-inch tile diameter for the laterals. So I'm moving on to the diameter of the main. Drainage coefficient's the same. Only difference is the main is draining the whole field. I know that's 40 acres. And so I take 1/2 inch per day times 40 acres, do all my unit conversions, and end up with an estimated flow rate of 0.84 cubic feet per second, which is a lot more than each of those laterals, but each of those laterals is just draining a small portion of the field, and the main line has to take all of the water from each of those laterals, plus get a couple of the edges in there. So, of course, it would be higher. All right, so then I put that information in here. Now, in this example, I'm going to say maybe I need a slightly larger tile line. So I'm going to select the 10-inch diameter roughness value, and I would correct that if I was way off later. And I end up with a 8.78 inches. So maybe I would correct it here and see if I could get down to like just actually 8 inches. But more likely, I'm still going to be at like 8.3 or 8.4 or whatever, even if I change that roughness value. So it's probably smart to stick with the larger roughness value and take this number and round it up to a 10-inch diameter, because here we're looking for what's the next commercially available size, and it goes from 8 inches to 10 inches. So there's that. So then I've got the layout that I already decided on. I used local guidance for the spacing at my preferred depth, and then I was able to use these equations to compute the size or the diameter of the lateral lines and also of the main. So there you go. And that's the end of that. All right, so we'll be doing a lab on this, and you'll be crunching through that process yourself. And it will be super great.